Good. So one reaction of alcohols that we're not going to go into any great detail about, at least in terms of mechanism, is dehydration. And just like the name implies, de meaning removing, the hydra coming from water, like hydrate and hydrophobic and anhydrous and all that sort of thing. So that means water. So it means the loss of water. And indeed, if you treat an alcohol with a catalytic amount of a strong acid, sulfuric acid's pretty common. Phosphoric acid would work also. I think you might see either. And there are even other acids besides this that could be used. But these are probably the most common ones that are used. Then it will dehydrate to form an alkene. And so you do need, on the carbon that bears the OH, you need at least one hydrogen on an adjacent carbon in order for this to work. If there are no hydrogens on adjacent carbons, then game over. The alcohol can't be dehydrated. But as long as you have at least one such hydrogen, then game on. The reason I said we're not going to look in too much detail as to the mechanism is because that was some of the stuff that we skipped in chapter 6, namely about the E1 and E2 reactions. Now, as I think would shock no one, there are a lot of similarities between the SN1 and E1 reactions. Like the SN1 reaction, the E1 reaction is unimolecular, so it would have the same type of rate law, first order. And indeed, the E2 reaction is a second order reaction. It's bimolecular, and it happens all in one step, just like the E2 reaction, just like the SN2 reaction does. But again, I'm not expecting us to go into, any level of detail with these elimination reactions. I just want you to be aware that elimination reactions are a thing, and that in particular, we can eliminate water from alcohols, at least usually. Let me see. Does having double bonds decrease the weight of a molecule? Well, it does relative to the alcohol, that's for sure, because you're going to be losing 18 AMUs when you lose water. So I don't know that the double bond is what causes that directly, though I think you'll find, other things being equal, the alkene will definitely have a lower molecular weight than the alcohol starting material. I'm not sure that's what you meant, though. I guess my one-word answer to your question, does having double bonds decrease the weight of a molecule? No. I mean, I don't think the double bond particularly affects the weight of a molecule, because that's just using electrons, right? And electrons have almost no mass compared to protons and electrons. Almost all of the mass is in the nucleus. But I do think that you'll find that the product of a dehydration will be a lighter molecule, lower molecular weight than the starting material. At least I can't see how it could be otherwise. Good, so just to give an example of this, I don't know, let's take a relatively easy one. Let's say that we took cyclohexanol, and if you were to heat this in the presence of a catalytic amount of sulfuric acid, or phosphoric acid, and it may mention heat. Sometimes you'll also see a triangle, by the way. That triangle is an abbreviation for heat. And if they put two triangles, it means heated a lot. But be that as it may, I would expect that that would lose water, and so the product would be cyclohexene. And of course, it doesn't matter whether you put the double bond here or here. It's the same thing, right? And a molecule of water is also generated. Especially watch carefully with OWL, read the directions. They might want you to make a separate sketcher and put a water molecule in it. They're really weird like that sometimes. So please be sure you follow the directions. But of course, as I think you're familiar with by now, we mainly care about the major organic product, which would be an alkene. And yeah, I think that's all I really need to say about that. I've given you some examples also. I think in the class notes I used 1-propanol. Could have used this as an example as well. If we heat this in the presence of sulfuric acid, or maybe here I'll put phosphoric acid just because I feel like it. And let's say we heated that up. And again, you only need a catalytic amount, just a drop. I would expect the major organic product would be propene. In cases where there's more than one possible product, for example, if we took 2-methyl-2-pentanol, let me figure out what that would look like. And we went to dehydrate this. Well, if you look at this carefully, you'll see there's now multiple types of hydrogens on adjacent carbons. There's this kind. That hydrogen is an adjacent carbon. And of course, the hydrogens on this methyl group are the same as the 3 hydrogens on that methyl group. All 6 of those hydrogens are the same. The way you know that is if you replace any of those 6 hydrogens with, let's say, a halogen, and you name the compound, they will all of them have the same name. So that's how you know they're identical compounds. But there's also hydrogens on adjacent carbons over here. So you could lose one of these 2 hydrogens, which are the same as each other, or you can lose one of these 6 protons, one of these 6 hydrogens. And so how do you know which it is that you're going to lose? And the answer is, well, the simplest way to state the answer is you're going to get the most stable possible alkene product, which turns out to be the alkene that is the most substituted. And we've defined the word substituted multiple times in the past. So I predict that we're going to get the product resulting from losing one of these 2 protons. And if you're ever not sure and you're concerned, well, draw both of them and compare them. So the product that you'd get from losing one of those 2 protons would look like that. And again, I've given you a step-by-step method in the notes to know how to draw, how to get the correct structure, how to get the correct product structure. What you do is you remove the OH and you remove one of the adjacent hydrogens and you put a double bond between those carbons. You have to, otherwise they won't be obeying the octet rule. So that's in the class notes. In the class notes, I give you a step-by-step method to get the right product structure. So that's one possibility. But what would we get if we took off one of these 6 hydrogens? Well, then you'd get that. And I think I can also prove to you if you took off one of the hydrogens in the top carbon, you'd get that. And those 2 are the same thing. If you're having trouble seeing that, then it might help if you made a molecular model. But these are the same compound. All I did is rotate it around this carbon-carbon bond. So you can see that this double bond is more substituted than this one. This one is a di-substituted double bond. That one's a tri-substituted double bond. So that's going to be the major product that you would get, and not this one, however you might choose to draw it. So that's important. That's an important thing to know, and you'll be able to practice that in the OWL questions. So if you want to know what you'll need to know, again, check the class notes. I've told you step by step, if you're given a question that has a dehydration of an alcohol, how to figure out what the product looks like, step by step. Like I said, basically you take off the OH, you take off a hydrogen in one of the adjacent carbons, and then you put the double bond between those 2 carbons that you just fiddled with. And that will be the structure of the product. And then if there's multiple possible products, because there's multiple possible types of adjacent hydrogens, the one you'd expect to be the major product will be the most substituted of all possible alkenes. And if you're concerned because you're not sure what that is, then draw them all out. Look at them all and then make your decision. And I think you'll agree this is the one that's the most substituted. So we can be confident that that's going to be the major product. What happens to the hydrogen that is not in the red circle? Well, that would be the one that if you removed, you got this product. So there's still an oxygen attached in the resulting compound. No, I don't see any oxygens here. So again, step by step, you remove the OH, you remove a hydrogen on an adjacent carbon, and you put the double bond between those 2 carbons that you acted on. And if there's multiple possible hydrogens like there is here, draw them all. And then pick out the one that's most substituted. So we've defined substituted before. More substituted groups have more non-H's attached. That's the definition we gave before. So if you look at this carbon-carbon double bond, there's 1 non-hydrogen, 2 non-hydrogens, 3 non-hydrogens. So that is more non-H things attached. Whereas this double bond, or this double bond, is the same thing. There's 1 non-H over here, 1 non-H over here, but in this side, it's both H's. So these double bonds are less substituted. So I would expect this one to be the major product. So if it asks you what the major product is, that's how you know. And if you're having trouble seeing, just draw all possibilities out like we did here. And then look at the structures and make your decision. The alkene that has the most non-H's attached to the 2 alkene carbons, directly to the 2 alkene carbons, that's going to be your major product. The other ones will be minor products. And again, actually, those two are the same thing. So what happens to this hydrogen? Well, it's still there. There's still 3 H's on that carbon, 3 H's on this carbon. Nothing happens to them. So you only take off exactly one of the adjacent H's. And again, I've put the step-by-step method in the class notes. You'll find exactly how to do it there. So that I think is enough for us in terms of dehydration reactions. Yes, there are other types of eliminations also, but since we're in a chapter on alcohols, I think this is the most relevant at the time. Good. Any other questions then about dehydration of alcohols? So bottom line, be aware that this is a thing that alcohols can do. And by the way, this type of thing happens in living systems all the time. There's both dehydration of alcohols to make an alkene, and then there's hydration of alkenes to make an alcohol, which we've already met in chapter 3 when we discussed how alkenes behave. So that's why you need to know this. That's why I think it's important, because reactions just like this occur in living systems. Granted, we're not using sulfuric acid. We have other ways of catalyzing these reactions, namely enzymes will do the catalysis for us. So that's one thing that alcohols can undergo. Let's move on then to discuss reactions with hydrogen halides. I also want to make sure we do the oxidation reactions. And then if time permits, I'll say a few words on basically polyols, so compounds that have more than one OH group on them, that's a thing. And I think we've really already talked a fair bit about thiols, but that I think will be enough. Good. So let's move on. There's another reaction of alcohols in which we can convert them to alkyl halides. And basically the way this works, I'm just going to give you the generalized reaction first, and then we'll look at some examples. So I have here a generalized alcohol. The other 3 bonds can be to whatever hydrocarbon groups you want. And essentially, we're going to treat this with a pure hydrogen halide. So no water, nothing else is present in the reaction mixture. And we're going to require that the halogen be chlorine, bromine, or iodine. HF will not react with alcohols. Its acid strength is too low. HF is a weak acid, but HCl, HBr, and HI are all strong acids. So we can expect that you will get the corresponding alkyl halide. So the step-by-step plan here is you look at where your OH is and you pull that off. Then you look and see which hydrogen halide you're given, and you put that halogen that you're given in place of the OH. And yes, you will also get a molecule of water as an inorganic side product. You will know by the phrasing of the question as to whether you need to show it or not. OWL might or might not want you to do so. Normally, we organic chemists focus on the major organic product, but that's the fate of the OH group. And I think you'll see actually that reaction is, as it is, balanced for mass. This plus HX gives this plus H2O. I think that's balanced for mass. So again, what you need to know, and we'll do some examples in just a moment, but just to summarize what you need to know, that if you take an alcohol, you can treat it with either HCl, HBr, or HI, and you will get the corresponding chloride, bromide, or iodide. It's the major organic product. Corresponding meaning that the carbon-halogen bond goes in exactly the same place that the carbon-oxygen bond is in the alcohol. So let's do some examples. 1-butanol. There's our 1-butanol. Reacts with HBr. And again, you really would add nothing else but pure HBr, which sounds to me like kind of a pain. I'm trying to remember if I've used pure HCl or HBr. I think I have. So they're gases at room temperature, and their boiling points are really low. So you need to get a gas cylinder and a cold trap and condense it in your flask. It's a pain. It can be done. It's just a pain. So again, remember our step-by-step method. You look at where the OH is, and then you look also at what halogen you're given in your hydrogen halide, and you just switch the two. It's a substitution reaction. I think you can see that. If you switch the halogen and the OH, you'll get HOH, also known as water, and the alkyl halide. So you just look at what halogen is in the hydrogen halide that you're given, and you simply replace the OH group with that. That's how you get the right answer. That's how you get the product. And yes, you'll also get a molecule of water. The wording of the question will indicate whether or not you need to put that. Right, let's do, does that make sense? Everyone see how I did that? Let's do another one, 1-methyl-cyclohexanol. This I like, really? This is better than the alkene one? Okay, I don't begrudge you that in the slightest. So here's 1-methyl-cyclohexanol. Let's treat this guy with HCl. I'm just copying straight from, and let's say that we treat this with HCl. So same idea. You look at where your OH is and you look what the halogen is that you're given in the hydrogen halide, and you just switch them. So I would expect that we would get 1-chloro, 1-methyl-cyclohexane. And yes, you'd also get a molecule of water. So that would be the expected major product. So bottom line, what you need to know is alcohols react with hydrogen halides, or at least with HCl, HBr, and HI. HF wouldn't work. HF is a weak acid. There probably is a way to convert an alcohol to an alkyl fluoride, but I don't know what that would be off the top of my head. But certainly HCl, HBr, and HI are fine. You will get the corresponding alkyl halide. Again, corresponding meaning that the carbon-halogen bond goes in the exact same place as the carbon-oxygen bond was in the alcohol. And that's basically it. And like I say in the class notes, we're not doing 7.10 and 7.11, except I do want to mention one important point with this whole idea, which is that phenols, wait a minute, ethyl alcohol and methyl alcohol are attached to cyclohexane. So you want something with more than one OH. So you want to make, what do you want? CH2OH. Am I doing this right? And then you want a hydroxyethyl group. We can do this, like this. Well, you would need to react it with an excess of the hydrogen halide. So you would want at least 2 equivalents. And it's best practice to mention that when you're using an excess. If you use only 1 equivalent, then the question can't be answered. There's no good answer to the question because you'd get a mixture. But as long as you used an excess, then yeah, I guess it, wait a minute, I didn't do that right. At least in principle. If you wanted a 2-carbon alcohol over here. But yeah, I think it would replace both of them. Reef will never be open. We're not having a reef session today for reasons previously stated. But I'd expect you'd get CH2I and CH2CH2I. So you do need to add enough of an excess of the hydrogen halide to react with any and all alcohol functional groups in the molecule. But you wouldn't want to add less than an excess because you'd get a mixture, and that's, like, by definition, not a good reaction. Normally, we like to get one clean product out at the end, to the greatest extent possible. So you couldn't ask the question, what is the one product that you would get if you used only 1 mole equivalent, because there is no the one product. You'd get a mixture. You'd get some of this, some with only that one replaced with iodine, some with only that one replaced with iodine, and some unreacted starting material. It'd be a big mess. But with an excess, then it's clear. then as long as you used, in this case, at least 2 equivalents, I would expect that you would get that. So good, I think that's all I need to say about that. How are we doing in time? Not quite 3:25. Oh, right, but I was gonna make the point about phenol. Phenol is an exception to this. Phenol does not react with hydrogen halides. Phenol and phenol derivatives, anyway. So if you were to treat this with anything, either HCl or HBr or HI, I would predict nothing would happen, no reaction. NR for no reaction. The reason is that the carbon-oxygen bond in phenol is very much stronger than for regular aliphatic alcohols. That's part of the reason. The other reason is this carbon can't react as easily being sp2 hybridized. We are depending basically on some nucleophile being able to attack that carbon, and you can't. The benzene ring's in the way. So I would say both of those are reasons why phenols do not react. Benzyl alcohol would. There we go again with that stupid word benzyl, but again, we're stuck with it. That's benzene CH2OH. That would react just fine with any of these alkyl halides. You'll get the corresponding benzylic halide. But phenol, any aromatic alcohols, any phenols, game over. Those don't react with hydrogen halides. No reaction. You just get the phenol out in the end. What was the second reason in simple words? Again, you're requiring me to have been listening to myself. Oh, because this carbon's sp2 hybridized, in order for the reaction to go, we need a nucleophile able to come into that carbon, able to attack that carbon, and the benzene ring's in the way. It can't do it. So, so I would say those are amongst at least the reasons why phenols don't react. Also because the carbon-oxygen bond is really, really strong, much stronger than in an aliphatic alcohol. We've defined aliphatic alcohols before. So yeah, that's just one exception that's technically in section 7.11, which technically are not responsible for. But I would like you to be aware of that one fact, that phenols do not react with hydrogen halides. You don't get aromatic halides from that. Good, other questions then? Well, in that case, I think the main thing that we have left is oxidation of alcohols, which there's a couple different possibilities. And I'd like to go over this I like to do this in the order from simplest to least simple. But in order to understand this also, I'm going to have to introduce you to 2 new reagents. They are both oxidizing agents. And both of them involve chromium. Wait a minute. Let's do this again. Where is chromium? Periodic table. I'll also need to switch over so the chat can see it. I want a video, images. It's maybe not the best one, but we'll make it work. All right, so now all of you in chat should be able to see this periodic table. So where's chromium? There it is. It's element number, crap, can't see a thing. Why will it not make the picture bigger? Getting cranky about this. Looks like it's 21, 22, element 24, I guess, chromium. Yep. So that's it. It's in the first row of the D block. So like a lot of these early to mid transition metals, these metals can get oxidized up to very high oxidation numbers. And as a result, you can get some really seriously strong oxidizing agents using those particular metals. So one of them is what's called Jones reagent. And frankly, we're mostly going to be focusing on these names, although I would like you to know, it'd be really great if you knew that these are both chromium reagents. And Jones reagent is effectively chromic acid. It's really like H2CrO4. And if you work out what the oxidation number is in the chromium here, let's see, hydrogen's generally +1, so we have +2 coming from the hydrogens. Oxygen's almost always -2, it certainly is in this case. 4 times -2 is -8. -8 and +2 makes -6, so the chromium has to be in the +6 oxidation state in order to cancel out the -6. So that's a very high oxidation number. It's a seriously strong oxidizing agent. And I would say chromium +6 and manganese +7. Those are amongst the strongest oxidizing agents known to man. And so this is not the only way it can be written. They might give you like Na2CrO4 plus sulfuric acid that will generate H2CrO4 chromic acid, as we say, in situ. It makes it in the actual reaction vessel. So very, very strong oxidizing agent. This is a strong oxidizing agent. Can I just go ox agent? And it's going to matter, at least for some of the reactions we learned, as to which oxidizing agent we use. There's also another one, which really deep down is also a chromium-6 reagent, called PCC, which stands for pyridinium chlorochromate. And I'll show you its structure. I don't suppose I care very much if you memorize this structure, but I'll show it to you anyway. So you know what pyridine is. It has, it's like benzene, except we replace one of the CHs with nitrogen. Pyridinium is the conjugate acid of pyridine. So it's got an extra proton on it. And the counter ion to this is ClCrO3 minus. And if you work it out again, this I think we'll find again that's chromium in the +6 oxidation state. So both of them involve chromium in the +6 oxidation state. It's just that in PCC, the presence of the pyridine and pyridinium buffers it. So it's a less reactive compound. So this is a mild oxidizing agent. So that's the main things I'm going to expect you to know. That Jones reagent or chromic acid is a strong oxidizing agent. It's going to be relevant in just a moment, at least sometimes. And then this other one, PCC, pyridinium chlorochromate, that's the one I'd like you to learn as being the mild oxidizing agent. It does pretty much the same thing, but it's not as reactive. It won't go as far. And again, that's because the pyridinium buffers it. So it's milder, it's less reactive. PCC is pyridinium chlorochromate. The job of the ClCrO3 minus is to be a counter ion to the pyridinium. So this thing is a plus charge, this thing is a minus charge. It basically acts like Na plus Cl minus. It's just an ionic compound. So the reason you need to put both, and again, I don't think I care very much if you memorize it, this is the structure. But as for pyridinium chlorochromate and its spelling, that will be in the textbook. You can find the spelling there. I don't really mind if you just learn it as PCC. It's a mild oxidizing agent. Both of these do involve chromium in the +6 oxidation state. So that's how you know they're oxidizing agents. That's really, really high valent chromium, very high oxidation number. It would very much like to lower that oxidation number to something more like +2 or +3. And indeed, that's exactly what's going to happen. And in the end of the reaction, you get this really disgusting, depressing, brownish chromium mud, which is disgusting and somewhat difficult to get rid of. But, you know, I've used PCC quite a bit in my life, and PCC reactions are quite depressing to run. But they work. In general, they work. Good. So as long as you're aware of these two reagents, I think we can go on. And with that, now the only thing that matters is going to be the type of the alcohol. So let me also put a heading here. This is about oxidation of alcohols. And the outcome of oxidizing an alcohol depends on the structure of the alcohol and may also depend on whether you're using the strong oxidant, which is a Jones reagent, or the mild oxidant, which is PCC. So, and again, I always do this in this order. I'd like to go from the simplest case to the least simple case. So the simplest case of all is when the alcohol is tertiary. And we've defined primary, secondary, and tertiary carbons, primary, secondary, and tertiary alcohols. Tertiary alcohols are the easiest case of all. And the bottom line here is game over. Tertiary alcohols cannot be oxidized, no matter which, whether you use Jones reagent or PCC. So let's take a typical tertiary alcohol. Well, how about that one we had before? 1-methyl, 1-cyclohexanol. That's a tertiary alcohol. Whoops. And the way we know that is by the definition of a tertiary alcohol. We need the carbon that the OH is attached to be tertiary. So there's only alkyl groups attached. There are no H's directly attached to this carbon. That's how we defined a tertiary alcohol. And you can treat this with either Jones reagent. I'm going to just go RGT for reagent, or PCC, doesn't matter. Either way, no reaction. So tertiary alcohols cannot be oxidized. So if you're asked about oxidizing a tertiary alcohol, the correct answer is no reaction. Those cannot be oxidized. That's the simplest case. The second simplest case, actually I didn't do it in order from simplest to least simple. So, but we will do that here. What about secondary alcohols? Secondary alcohols can be oxidized. And let's, as an example, look at, oh, I don't know, what about 2-pentanol? That's a secondary alcohol. That fits into the definition. Can any molecule in which CR is oxidation number 6 be Jones reagent? No, it's pretty much going to be chromic acid. But like I said, you can just write Jones reagent. I'm fine with that. I would like you to be aware that it's chromic acid, but and certainly that it's the stronger oxidizing agent. But the main things that I want you guys to know are that both chromic acid, Jones reagent, and PCC involve chromium in the +6 oxidation state. But Jones reagent, the chromic acid, is the stronger oxidizing agent, and PCC is the milder oxidizing agent. That's really, if you have that down, I'm happy. I really don't care if you memorize those structures. Good. So here's an example of a secondary alcohol, which again, we've defined. It means an alcohol where the carbon attached to OH is secondary, which this one is. There's one H and 2 alkyls attached. So in the case of secondary alcohols, it's actually pretty simple. It doesn't matter which of the 2 reagents you use, whether you use Jones reagent. There's a joke in there about having a Jones for something, but I'll leave that to the rest of you. Or PCC, doesn't matter which one you use. In either case, it oxidizes the secondary alcohol to a ketone. And I put the step-by-step method for getting the right answer in your class notes. Basically, the bottom line is you remove an H from the alcohol oxygen, and you also remove a hydrogen from the carbon that has the OH attached to it. So it's this one over here. You remove those 2 H's, and you make a double bond between carbon and oxygen. That's the answer. So either way, whether you use Jones reagent or PCC, on a secondary alcohol, the product will be the corresponding ketone that you get by removing 2 H's. And that's actually not a bad way of thinking of the reaction. It's an elimination of H2. You can think of it that way. That's certainly correct. And in the end, you go from a secondary alcohol to a ketone. And again, it doesn't matter which of these reagents you use. That's the only possible outcome. So I was going to say something else about this. I forget what. Oh, here's another interesting thing. This carbon over here turns out to be chiral, doesn't it? Oh, that's mean, using something from a past exam. Sorry, but it's chiral. We've got H-methyl-OH and a propyl group. But interestingly, after the reaction, it's no longer chiral. Now that carbon is sp2 hybridized. Remember, our definition of a chiral carbon is 4 different groups attached and sp3 hybridized. That's sp2 hybridized, so game over. So that's something that's pretty commonplace with this type of reaction. You can convert a chiral compound to an achiral compound. That's not unheard of. Earlier, we talked about cases where you start with an achiral compound, but your product is chiral. This is the opposite. It's very possible to start with a chiral starting material, but you lose that chirality in the product. The product is achiral. That's just something interesting that can come out of all this. That was the other thing I was going to say. It turns out that having that hydrogen attached to the carbon bearing the OH is pretty key. You need to have at least one hydrogen attached to the carbon bearing the OH group. And that's the reason, by the way, why tertiary alcohols cannot be oxidized. There's no hydrogens on that carbon. So it can't be done. There's no way of oxidizing a tertiary alcohol. So it's not just like magic or something that these reagents have no effect on it. It can't be oxidized because you need a hydrogen there, and there is none. So you can think of it that way. Okay, what about primary alcohols? That's when it matters which reagent you use. And a good primary alcohol might be, and what about 1-hexanol? 1, 2, 3, 4, 5, 6. There you go. That's a primary alcohol. Here it matters which reagent you use. If you treat a primary alcohol with our milder oxidizing agent, which is PCC, that will oxidize the alcohol up to an aldehyde and no further. It stops then. So the step-by-step method here looks pretty much like for secondary alcohols. You look at your alcohol, you take off the H from the OH group, and then one of the 2 adjacent H's on that primary carbon. You take those 2 H's off and you turn the single bond into a double bond. And you'll find that you get an aldehyde. So primary alcohols, when that's an H, by the way, although you'd be hard-pressed to know it. Goodness. There, that's a little better. So primary alcohols react with, this is only one example. I could have picked any primary alcohol, but they react with PCC to form the corresponding aldehyde and then stop. There's no further oxidation. Even though further oxidation is in principle possible, PCC doesn't oxidize primary alcohols any further than the aldehyde. Meanwhile, if we took the same primary alcohol, 1-hexanol, and we treated this with Jones reagent. That's our strong oxidizing agent. Jones reagent will oxidize a primary alcohol all the way up to the corresponding carboxylic acid. Whoops. So the step-by-step plan there basically involves finding the carbon that your OH is attached to and just changing that carbon to a carboxylic acid carbon, COOH. So again, you find the carbon that has the OH directly attached and turn that carbon into a carboxylic acid, and then you're done. Phenol can be oxidized. No, phenol cannot be oxidized. Phenol is essentially like a tertiary alcohol, in a sense. Let me write it with the double bonds. Good question, but answer is no. There's no hydrogens on that carbon, so there's no way to oxidize it. I don't think phenol itself can be oxidized. If you start talking about hydroquinone, now we're getting somewhere. Where do you get 2 oxygens from? They come from the Jones reagent, and there's also water in the mixture. So the 2 oxygens come from the reagent. Actually, 1 oxygen, right? We only really need 1 more oxygen. So that's where they come from. We're not violating the law of conservation of mass here, I promise. So there is one other thing also. Jones reagent will also oxidize an aldehyde to the corresponding carboxylic acid. So you could do it either way. But PCC will not. PCC will not oxidize an aldehyde any further. And if you treat a primary alcohol with PCC, you get it goes to the aldehyde and no further, doesn't get oxidized any further. Jones reagent will oxidize either an aldehyde or a primary alcohol all the way up to the corresponding carboxylic acid. And I've left step-by-step methods in the class notes that show how to get from either the primary alcohol or the aldehyde to the carboxylic acid. But basically, I've already said that if you're given a primary alcohol in Jones reagent, you find the carbon attached to the OH and you change it to a carboxylic acid functional group. You change that same carbon to a carboxylic acid carbon. From an aldehyde, it's even a little easier. You find the aldehyde carbon, oh, I love these questions, just a minute. And the aldehyde has a hydrogen, you just change that hydrogen to an OH and you're done. So that's really the only complicated one, where it matters whether you use PCC or Jones reagent. For tertiary and secondary alcohols, it doesn't matter. Can we oxidize cyclohexanol? Well, let's look at it. So what kind of alcohol is cyclohexanol? Don't forget we do have an H over there. I hope you're coming to the conclusion that this is a secondary alcohol, just like 2-pentanol was. So sure, we can oxidize it. And in this case, it doesn't matter what you use. You can use either PCC or Jones reagent. And remember our step-by-step method. You find the carbon that has the OH on it, you take the H off the O and the H off the carbon that's attached to the O, and then you make a double bond. And I think you'll agree we go from cyclohexanol to cyclohexanone. Ooh, that's terrible. Turble, T-U-R-R, bull. There we go, that's better. So sure, you can oxidize that. You can oxidize any primary or secondary alcohol, but secondary alcohols, the only possible oxidation product is the ketone. And it doesn't matter if you use Jones reagent, same result, you'd get cyclohexanone. Primary alcohols, now it matters which of your two oxidizing agents you use. Primary alcohols react with PCC to make the aldehyde, and then it stops, doesn't oxidize any further. But primary alcohols react with Jones reagent to go all the way up to the carboxylic acid. And actually, it goes through the aldehyde, right? It first oxidizes the primary alcohol to the aldehyde and then keeps going and oxidizes the aldehyde to the carboxylic acid. Any oxygens that you need for the reaction are going to be in either the Jones reagent or the solvent. This is usually done in an aqueous system. So there's water around also. And actually, I think I'm out of time. So I think I'd better leave it there. But we've already talked about thiols, and I gave a few words on alcohols with more than one OH group. That's going to become relevant when we get to the chapter in carbohydrates, because that's what carbohydrates essentially are. They're just things with lots and lots of OH groups. But I'm out of time, so I will leave it there, and I will see you all on Friday.